It's a great honor for me to share with you some experiences of using an artificial intelligence tool with real applications in the field of engineering. I regret that I will not be able to be present due to previously acquired commitments. The technique I am talking about is multi-objective optimization, which was born at the end of the 19th century by Vilfredo Pareto in the context of economic problems, but its use has spread to all branches of technology. Multi-objective optimization is not usually seen as an artificial intelligence tool, but from the perspective of its alternative name, multi-criteria optimization, or better still, multi-criteria decision techniques, we are beginning to see how it can help engineering decisions in both design and operation. Beyond their function as a decision-making tool, the computational algorithms used to solve them, such as genetic or ant colony algorithms, are tools belonging to the artificial intelligence. Although optimization from a mathematical point of view is a well-known topic, let me give a very brief introduction to the subject.
When there is only one objective to optimize, the idea is simple. Find the global maximum or, more typically, the minimum of the objective function f of x, where x is the decision variable constrained by equality or inequality restrictions. F is also called cost function or evaluation function, and x prime is the value of the decision variable that minimizes f. But what happens when there is more than one objective function and they compete with each other, as is usually the case? For example, if we have these two cost functions, f1 and f2, each of them has a clearly identifiable minimum. But if we have to regard both at the same time, we will not have an optimal value, but a zone, a set of optimal values called the Pareto set optimal set. According to Pareto, this set consists of all those non-dominated individuals such that a variation in one of the decision variables will cause an improvement in some cost function, but a loss in at least one of them. All the values in that set are optimal, and then we will have the work of choosing within that set a preferred solution that we will finally apply. It is very common to have more than one decision variable. For example, in the optimization of the use of air conditioning, shortened HVAC, we have two decision variables, the cooling set point and the air speed in the room. Also, there are two competing objectives, comfort, because in warm areas we have to lower the set point of the air conditioning to achieve better comfort, and energy use, which works the other way round, since if we want to reduce energy use, we have to increase the temperature set point. We will come back to this example later. First, I want to share an application of multi-objective use in device design. Take, for example, the design problem of a hydrocyclone, which is a particle size classification device for particles entering tangentially into the hydrocyclone. The decision variables are those that define the geometry of this device, heights and diameters, 5 in total. Obviously, there are infinite possible combinations. How to make the decision? A hydrocyclone model allows us to find its efficiency curve, taking into account certain decision variables and operating conditions such as flow rates, pressures, and densities. On the horizontal axis, we have the particle size, and on the vertical axis, the weight fraction that will go down the under. The core size will all go down the under, and the fines will go out the over of the hydrocyclone. We have solved the problem by posing three competing cost functions. First, a function that measures the quadratic distance from the obtained mean particle diameter to the desired mean diameter. When the multi-objective algorithm minimizes this function, it will accommodate the decision variables so that the actual mean diameter matches the desired mean diameter. Second, a function that calculates the inverse of the derivative of the separation curve at the point of the mean particle diameter. This ensures the size separation is as sharp as possible at the mid-diameter point. Finally, there is a function that simply measures the water bypass to reduce it as much as possible. This technique has reduced the values of the objective functions that were achieved manually in the order of 10 to the fourth to 10 squared. Thus, we have designed a much more efficient device.
This example is a design problem, and is static in the sense that it is computed for a set of conditions that are assumed to be stationary. However, multi-objective optimization has a particular power when it is used to find the best time trajectory of operating a device that has already been designed. This involves evaluating functions that are not static but have a path over time.
The previously stated problem of multi-objective optimization of thermal comfort and energy consumption can be solved with this approach. The key idea is to run the process model in time in a predictive way against certain control actions, and then evaluate the trajectory to see if it dominates other solutions. We define two basic cost functions, one for energy consumption, where UA is the binary start-stop signal of the HVAC compressor in the prediction horizon from NW1 to NW2. The second function is to reach a certain target in the percentage of dissatisfied, which can be measured objectively. This function is also predictive up to horizon NW2. When a multi-objective calculus of the different sequences of decision variables, a Pareto profile like this is obtained. Obviously, lower percentages of dissatisfied will require higher energy spending and vice versa. Each of the points of the Pareto profiles relates to a time sequence of cooling setpoint values and ventilation rates. If we take three typical possibilities, the one with the lowest energy, the one with the lowest percentage of dissatisfied, and the intermediate one, the time evolutions are on the right side of the image. Solutions with fewer dissatisfied, such as solution 3, require more energy spending, which results in a lower HVAC setpoint, as we have already seen in the Pareto profile. Solution 1 is a trade-off alternative that is always very efficient. This table shows that solution 1 shows a saving of almost 70% compared to having the set point constant at 24 Celsius degrees during the whole working hours. In conclusion, it can be clearly seen how multi-objective optimization acts as a decision tool for time trajectories in the operation of systems. Let us now see the case of optimal operation of a column flotation unit. This is a device that improves the concentration of a certain mineral by draining it through bubbles that travel from the collection zone to the cleaning zone and then to the concentrate. The decision variables are the height of the cleaning zone, the gas holdup of the collection zone, wash water flow rate, and two reagent flow rates, the collector and the frother. K is a time index. The goals are: maximize the profit. This is obtained as the market selling price of the product minus production cost. That prevents the concentrate grade from being lower than a minimum. That prevents the density in the froth from growing above a maximum. That sets an internal bias flow between a minimum and a maximum. Finding the trajectories over time of the decision variables that achieve these goals is a predictive multi-objective optimization problem. The solution to this problem is shown in this block diagram, where the supervisor feeds back not only the local variables, but also the market conditions to find better trajectories for the decision variables. When these objectives are translated into mathematical expressions similar to those already seen in the case of optimizing comfort and energy use, results like the one shown in this image are obtained. On the left, we have the decision variables, and on the right, the objectives. It can be seen how from a non-optimal operating point defined by a human operator, there is an increase in the profit, the concentrate grade remains above a minimum of 0.75, and the froth density does not exceed the maximum permissible of 0.4. The bias flow rate, which starts negative, indicating a malfunction, quickly recovers to a slightly positive value. In this other situation, we see the optimal supervisor's response to a drop in feed grade. As there is less reach over input per unit of time, there is logically a drop in profit. However, an initial drop in concentrate grade is quickly recovered. It is also observed how an increase in froth density is fixed by the system. The same applies to the bias flow rate, which has an initial fall but is also restored to optimum values. Here is a third example of the response of the optimal supervisor to an increase in feed flow. As expected, there is an increase in the process grade. The product quality values are kept constant. Likewise, the values of froth density and bias flow rate are kept at admissible values. In summary, the flotation column operation example shows how multi-objective predictive monitoring is effective in making decisions on trajectories to be followed by the variables of a system. Let us look now at the optimal predictive solution to the problem of blending multiple sources of minerals that are fed into mineral processing plants. This problem involves the blending of different sources of ore like open pit, underground, and stockpiles, several plants of treatment, and different final products. In this case, we are going to look at the gold and silver mine, so we have two output products. There are 10 different sources of ore. Each of these is defined by a flow rate in tons per month, a gold grade ore concentration, and a silver grade. These values can change over the life of the mine, which we will say in n months. Furthermore, these flows can go to a mill processing plant, a heap leaching plant, or an intermediate stockpile. The heap leaching plant has a recovery of around 50% and a high processing capacity, in this case 100,000 tons per month. It is a low-cost process. The grinding plant, on the other hand, has a high recovery of around 80% for gold and slightly less for silver, but has high operating costs due to the high energy consumption of the grinding process. This suggests that the richer veins should be fed to the milling plant as it has a higher recovery, while the lower grade streams should be sent to the heap leach plant. This is a good first approach, but there are too many variables involved. The market value of the metals, marketing costs, labor and reagent costs, all varying over time. Even the weather forecast comes into play, because if there are high winds, the open pit operation is suspended and only the underground mine is operated. How do we ensure that a particular combination of flows will produce the highest profit for the company over time? In its simplest formulations, and when the problem is solved statically, that is to say, not predictively until the end of the mine's life, linear programming is typically used. However, in its entirety, it is a non-linear problem, and since it involves integral variables such as the indices that identify the ore sources or the processing plants, it is actually a mixed integer non-linear program problem. Again, multi-objective predictive optimization provides an alternative, powerful and flexible way of solving the problem. As in the other examples we have looked at, the strategy focuses on the design of the objective functions. The vector of decision variables includes the flows to be extracted from the mine, the flows from the stockpile to the treatment plants and the current time, and the destinations of these flows all at the current time, then at the next time interval, and so on until the end of the mine life. Once the optimal value of these decision variables has been obtained, only those of the first time are used, and the process is repeated at the next time of optimization, as is typical of predictive control. About the objective functions, the most important one is the maximization of the overall profit of the process. Second, a function designed to lead the gold product as close as possible to the production objective. Third, this function aims to fully consume the mine's reserves by the end of the projected life period. Then, two functions ensure that the milling and heap leaching treatment plants are always used to their maximum capacity. only one restriction is used, with the objective that the stockpile content never falls below an admissible minimum, as the metal content of the stockpile is related to the financial assets of the company. This figure shows the time evolution of an actual application example using a 24-month horizon. The gold grades of the different ore sources range from 2 to 12 grams per ton, but they show a sharp drop in their forecast in month 8. It also considers the forecast of a 13% increase in the gold price in month 16. The milling plant has a capacity of 50,000 tons per month, and the heap bleaching plant has a capacity of 100,000 tons per month. The stockpile must not fall below 20,000 tons until month 20, when the mine begins to close. On the left, we have the evolution of the flow rates to achieve the proposed objectives. If 1 is the milling plant index, 2 is the stockpile, and 3 is the heap bleaching plant, the destinations change from D1 for the first 7 months, D2 for months 8 to 15, and D3 for months 16 to 24. The optimized solutions obtained show an increase in profit of between 5% and 10% over the solution calculated by a trained mine programmer. The maximum and constant use of both plants is observed, the minimum stockpile volume is complied with, and the depletion of reserves at the end of the project is ensured.
I hope that with these 4 examples of use, 1 static and 3 dynamic, we can see predictive multi-objective optimization as an effective decision-making tool. The versatility of predictive multi-objective optimization is remarkable. Very simple evaluation functions can be used to solve very complex decision problems, which are often non-linear and combine real and complex numbers with integers. Multi-objective optimization problems are solved with easy-to-learn heuristic tools. The secret lies in a good design of the objective functions. Thank you very much.